Okay, thank you. Thanks for introducing me. Thanks for inviting me, and thanks for organizing this seminar and yeah, keeping this up and running. And so I mostly found it very interesting, and unfortunately I cannot come by as often as I would like to. But nonetheless, I found there were lots of interesting talks in this seminar, and it's great that you keep this up and running. So what I will be talking about is yeah, a couple of results that I was able to come up with together with various other researchers, where monomial parameterizations of the steady state equation of the steady state variety helped a lot in the analysis. And so my motivation was to tell you a little bit about these parameterizations and how we could use what properties how we were able to exploit them. And so I will start with an introduction where I just lay out the notation, and yeah, I guess many of you will know these slides. I use these introductory slides in almost every talk where I set up the notation. Then I will comment on monomial parameterizations, how you can find them. And I will briefly talk about two applications to elucidate dynamical properties, namely multistationarity and Hopf bifurcations that are possible using these parameterizations. And finally, I will have a summary and conclusions. So let's start with the introduction. So I consider throughout this talk ODEs defined by a reaction network with mass action kinetics, and these have a very nice form. They are given they are given in terms of a matrix S, the stoichiometric matrix. This is a matrix that contains numbers, that contains usually integer numbers, and a vector R of reaction rate, and this is a vector of monomials in the unknowns K and X. And the monomials are of a very special form. They are linear in the Ks. These Ks are the rate constants and one set of parameters that one can consider when studying these systems. And throughout the talk, I assume that the matrix S does not have full row rank, meaning it has a non-trivial left kernel, and that there exists consequently a matrix Z that spans this non-trivial left kernel. And this assumption, this setting has a consequence concerning the solutions of the ODEs. Every solution, given this matrix Z that sort of spans the left kernel, every solution, if I multiply any solution with this matrix, then it evaluates to a constant in time. And this constant is defined by the initial conditions. And these constants, they have a special biochemical meaning. They are total concentrations, conserved moieties. And I think they are very important parameters in studying the systems, because sort of the dynamics depends on, you can have different dynamical behavior for different values of the Cs. And I like to use them in application studies and things like that, because as a set of parameters, they are easier to modify biochemically than the rate constants. And so I think they are good candidates for doing this kind of analysis. And what this means geometrically, I have drawn a picture where I try to depict this. Geometrically, this means that every trajectory, every solution with a given initial condition is contained in an affine linear subspace that is identified by the value of the total concentrations. This is simple triangle here, and now every these triangles, they're invariant. You start for time 0 in one of these triangles, and then you stay in these triangles for as long as the solution exists. And this is important when we are talking about, for example, steady states. Steady states are constant solutions, are solutions that are defined by the polynomials, by these polynomials S times R. And I like to look at a certain set set of steady states, because I like to treat these rate constants as fixed but unknown. So I like to think of this variety as something that is living in the space of concentrations as well as the space of rate constants. And in all the systems that I consider and throughout this talk, this variety will have a positive dimension, and often, in many cases, the dimension is complementary to the dimension of the stoichiometric subspace. So this variety, if you want, it contains infinitely many steady states. However, a given solution, a given trajectory does not care about the whole variety. It only cares about those that are contained in its particular stoichiometric class, in its particular triangle. And I try to put this triangle here again, so sort of as a reminder. So the trajectory, wherever I start in this triangle, it actually only cares about these 3 points that I have depicted here, and not about whatever the dimension or the shape of this variety. So actually what one is studying is the intersection of these stoichiometric classes with the variety. And the means to do this is this polynomial system that consists of the steady state equations and the linear equations defined by the conservation relations. And then, for example, one question is, are there values of K and C such that, for example, there are multiple steady states, or for example, such that there is a Hopf bifurcation. And this brings me to the two properties that I have studied so far. First of all, it's multistationarity, which means that there are at least 2 positive real solutions for some value of K and C. And usually, so there is one value of C, and for this, we want to have at least 2 solutions. And usually if we have established this and found rate constants and total concentrations and do some numerical continuation, then we usually see, if we vary a total concentration and plot the steady state concentration, then we usually find a region where we have several steady states, and we get this S-shaped curve that are of interest in modeling, for example, signal transduction systems and the like. And another interesting property is the occurrence of a Hopf bifurcation. And what we're doing here is basically we look for an element of this variety for a steady state, and then we vary one of the rate constants, for example, and consider the Jacobian matrix of the system. And specifically, we monitor the eigenvalues, and then one has a simple Hopf bifurcation. If one pair of complex conjugate eigenvalues of the Jacobian crosses the imaginary axis, it goes, basically the real part goes from negative to positive, while other eigenvalues remain with negative real part. And this is of interest because nearby, close to this point, you can have oscillations, you can have a limit cycle, and if the bifurcation is supercritical, then you have a stable limit cycle. And this is what is depicted here is a simulation that I did for various rate constants close to one of these bifurcation points, and one sees that the blue curve seems to approach one such limit cycle. Okay, this was the motivation and what I will look after, and sort of the property that we exploited in establishing these dynamical properties were the monomial parameterizations. And I'd like to introduce them by means of an example. So consider this very simple reaction network having 2 species, A and B gets converted to A. If we look at the steady state equations, you see them on the left, and one notices that there is actually just one equation And this is a quadratic equation that we can solve. And we find two solutions. One is where xa is 0 and xb is any positive value. And the other one is more interesting. Is basically, it gives us xb parametrized by the xa. And if we put the two together, we get the parametrization. Every positive steady state of this system is of the form xa, and then along this line defined by with the slope k2 over k1. So this vector on the right-hand side here, this gives a parameterization of all positive steady states of the system. And yeah, I'd like to mention that sort of parameterizations exist for many reaction networks, and they need not be monomial, but the ones that I have been most interested in were those monomial parameterizations. In the paper, together with Thomas and Alex, we wrote a formal definition of when we say that a system admits a monomial parameterization, and this is equivalent to saying that there exists a rational function that depends only on the rate constants and a matrix, usually an integer matrix A, such that you have a solution to the steady state. Every positive solution of the steady state equation can be written by this formula here, where you have this psi times psi to the A. And I need to explain this formula. So the psi is the rational function that depends on the rate constants. It comes from the network. The psi are the free variables, the free objects in the parameterization. And the A is a matrix that defines the monomials in the parameterization. Every column of A defines one monomial, one psi monomial. In the previous example, we have seen that the steady states are on this form where I have replaced the xa with the xi. And if we look closely, we see that we can factor it in terms of this xi, which is just the vector 1 and k2 over k1. And this monomial vector, which is in this case is very simple because we have just the linear monomial xi. But nonetheless, the exponent is 1, 1, and this exponent goes into this matrix. So this parameterization, as every monomial parameterization, gives rise to these two objects, the rational function in the rate constants and the matrix. And now I'd like to comment a little bit on how to find this parameterization. In practice, sort of what I usually do is I just use Mathematica to simply solve the steady state equations. And the way I proceed is I compute the rank of the stoichiometric matrix, and if this is S, and then I basically solve the steady state equations for S out of the n variables. And sort of this is my experience tells me that if there is a monomial parameterization, then Mathematica will find it in seconds. If it doesn't find it in seconds, then I change the choice of variables. I do this a couple of times, and then usually I either find one or I'm almost convinced that it doesn't exist. But if I want to show that it doesn't exist, I will talk about this on the next slide. So usually it might sound I won't say complicated, but it might sound difficult to find, but actually experience tells if it exists, it's quite straightforward to identify. And my experience, this worked for systems up to like 20, 30, 40 variables. An example, one of the earliest parameterizations that I came upon in my career was when I was still a PhD student, was this two-side phosphorylation system, distributive two-side phosphorylation system. It's a system with 9 variables and 3 conservation relations. And so by playing around, I discovered that if you, for example, solve for these 6 variables, you get this very nice parameterization. And if you look carefully, you can sort of read off the matrix, the vector psi and the matrix A from this So if you, in the case that you don't find one, and if it might not exist, and you want to prove, one way to prove that there is no such is to compute a reduced Grübner basis, because sort of this, we find sort of a system, this monomial parameterization exists if and only if this reduced Grübner basis satisfies certain conditions. So basically, we compute the Grübner basis and look at its component. It will consist of several components. We look for the components that intersect the positive orthon, and if there is only one component, and if this special component is binomial, then there exists a monomial parametrization. So there is a way to tell whether or not there is a definite way to decide whether or not this exists. However, this is computationally expensive, and I rarely proceed this way. One thing that I wanted to mention is sort of if you want to establish a parameterization for, say, a family of systems where you don't have a fixed number of equations, then computer algebra is only of limited help. And one way I found that one can one has a chance to find a monomial parameterization is by looking at the graph of the network and then doing something that Matthew described in his paper, the translation. So and this works sometimes for some of these in my experience, or the experience I have, this worked very well for post-translational modification networks. What I've shown here is a particular network where you have a protein that is phosphorylated n times in a processive way, and using this translation described by Matthew, you can transform this into an equivalent graph, in a graph that defines an equivalent system of ODEs. And this graph has the nice property that it has only one connected component and that it is cyclic. And now one can apply basically something that Jeremy Gunawadena described in his 2009 paper. An idea that is based on the matrix tree theorem. You can look at the equation and use this lemma in their paper and come up with a monomial parametrization. And here, this is a parametrization that I found, Anne and I found in a paper. And basically, this is again in this form. The psi is now these rows. These are sums of these are polynomials in the rate constants, and there is some free parameters. So these parameterizations can be found sometimes by studying the networks, and in this case, you can sort of find them for families of networks. I'd like to conclude for this n-side system. Sort of, it was clear that such a rational parameterization would exist. This follows from Jeremy's paper. However, sort of was not clear that there exists a monomial parameterization. And this approach, as I said, I tried this with other networks from the family of post-translational modification systems, and I found that one can analyze, one can derive these parameterizations for different of these networks. And I'd like to conclude this part by stating that sort of the existence of parameterizations, not necessarily monomial, is guaranteed for several classes of systems that have been described by Jeremy, by Alicia and Mercedes, or by Carsten and Elisenda. So there's various classes of systems where it's clear that parameterizations exist. And this brings me to the final part of my talk, the monomial parameterizations and qualitative dynamics. And I'd like to start with multistationarity. And so the next couple of slides, I will talk about a reaction network where we have found a monomial parameterization. And we will need, from this parameterization, we will need this matrix A. Remember, as I said earlier, sort of if you have a monomial parameterization, then we have these two objects, the function psi and the matrix A. And to state the conditions, we will need something that is, we'll need a sign pattern. We will need to define what we mean if we talk about sign patterns of a linear subspace. For example, take the linear subspace. So the idea is that if you have a linear subspace, then this, even though it contains infinitely many vectors, it intersects only a finite number of orthons. And basically we care about the sign of all elements of the linear subspace, and as it every subspace only intersects a finite number of orthons, there is only a finite number of sign patterns that that correspond or are given by this linear subspace. And a simple example is this: if the image of S is spanned by this vector -1, 1, then if you picture this in R2, this is basically the image of this subspace is a line that goes from the top left quadrant to the bottom right quadrant. And basically every vector in this subspace either has negative first coordinate, positive second coordinate is 0, or has positive first coordinate and negative second coordinate. So this linear subspace, the image of this linear subspace, corresponds to these three sign patterns. And so there is a condition for multistationarity that involves these sign patterns that has been described in a couple of papers. One of the first references is my paper with Mercedes, Alicia, and Anne, and we have then sort of extended this in a later paper together with Stefan and Georg and Elisenda. And basically, the statement is, so you take these two matrices, these two linear subspaces, the image of the transpose of A and the image of the stoichiometric matrix. You compute all of the sign patterns, and then you check whether or not they have a sign pattern. There is a common sign pattern in both of them that is not the zero vector, because every linear subspace contains the zero vector. So you always find the zero vectors, but you're interested in a sign pattern that is not the zero vector. And this is an if and only if condition. So you have multistationarity if and only if this condition is satisfied. And the nice thing is this is independent of the rate constants and the total concentrations. All you need is the matrix A and the matrix S. And what I also find appealing is that it, if you want to decide this property, you can do this by solving linear inequality systems. You might have to solve a lot of inequality systems, but nonetheless, this is linear inequality systems. And for linear inequality systems, you can, for example, find certificates that they have no solutions. So in effect, using this result, you can give a proof that the property multistationarity does not exist. And I find this appealing and beautiful. That's one of the things I like about this result. Let's do it for this example. Now we have this simple system: A plus B goes to A, that we looked at on the previous slides, given the stoichiometric matrix and the matrix A. And the image of the stoichiometric is just this this line given by the vector -1, 1. So we know its sign patterns. The image of A transpose is just the line spanned by the vectors 1, 1. And so it's clear that every element is either has either two positive entries, two negative entries, or is 0. And if we compute the intersection of these two sets of sign patterns, we see that they only intersect in the zero vector. And so basically this is a proof that this network does not have multistationarity. For this particular network, this is a little bit of an overkill because this is a deficiency zero network, and so it's clear that there is no multistationarity. However, you can apply this to larger networks that are not efficiency zero, and then sort of you can derive more interesting results.
Excuse me to interrupt you.
Yeah.
You have 5 more minutes, including questions. I'd like to.
Oh, good. Okay, I have 2 more slides also.
Thank you.
Okay, so the idea with the Hopf bifurcations, this is something that I recently took up, or recently started to work on, and the idea is to use this monomial parametrization and to combine them with Hurwitz matrices. Hurwitz matrices are defined by the characteristic polynomial of the Jacobian of a system. And if we have a parametrization of the steady states, we can evaluate the Jacobian at this parametrization and then obtain the coefficients of the characteristic polynomial, and these Hurwitz matrices evaluated at this a particular state at all steady states. And the idea is that to exploit the theorem of Young from 2002, that basically is a sufficient and necessary condition for a simple Hopf bifurcation. And this basically asks you that all Hurwitz determinants are positive, and one of them is 0. And so the idea is, applying this idea is challenging, but it's challenging mainly for computational reasons, because if you compute these polynomials, they are huge. They're polynomials in the unknown case and these parameters of the parameterization, and they are huge. And by huge, I mean they can be like thousands of terms. And then finding points where these sign conditions are satisfied can be challenging. But sort of the systems I have been looking at, maybe we were lucky, maybe there is some underlying structure that these systems have in common. But for these systems, most of the determinants were polynomials that contain only positive terms. So it's trivial to establish that they are positive for positive parameter values. And only the one polynomial that I want to be 0, only this polynomial contained negative terms. And so it was straightforward to find points where these conditions are satisfied by looking at vertices of the Newton polytope. And so we were able, together with Maya and Anne, we applied this the first time to a mixed system of processive phosphorylation, distributive dephosphorylation, and we found these Hopf points and could show the oscillations numerically. And together with Anne, Nida, and Xiaoshan, we applied this to somewhat larger motive of ERK regulation. And together with Maya and Elisenda, we looked at subnetworks of the double phosphorylation system and could use this idea to show that these subnetworks cannot have Hopf bifurcation. This brings me to the last slide. So I'd say monomial parameterizations are helpful. Many systems that I found admit a parameterization, and they have 2 interesting applications. You can use them to decide multistationarity, and you can use them to study Hopf bifurcations. So I personally consider them an interesting and useful tool. Some of the publications are here, and with this, I'd like to thank you for your attention.